Hello. Today I'm going to talk to you about the law of conservation of energy, one of the fundamental pillars of the structure of physics. If you're talking about classical physics, which is what we study in this classroom, we're talking about things like Newton's laws of motion being one of those pillars, and the law of conservation of momentum. But in many respects, the law of conservation of energy is sort of the main structural support for the overall structure of physics. You could say that actually it's the overall structural support for all of science, if you really wanted to, because the law of conservation of energy dictates a lot of things. For example, I just read an article about a year ago about how the law of conservation of energy dictates how memories are made in the human brain, which is a pretty interesting concept, but not something that you would normally study in physics. Of course, you probably came into contact with the law of conservation of energy first in chemistry, because the heat energy that you put into a system, you could track where it went after you put it in, and then you could make it do work and such. All these different things, probably things you studied in chemistry. If not, that's okay. We will talk about that briefly in physics here. And it's going to this law of conservation of energy is going to be something that we refer back to for the rest of the year. So I want to make sure that you've got a good foundation in it. It's actually quite simple once you wrap your head around it. So let's take a look at it here. The definition of it says, at least my version of it, says in an isolated system. Remember, isolated means a system that is blocked off from the rest of the universe. The environment around it cannot add anything or take anything away from the system inside of it. So here I've drawn this system, just a mock-up of it, of course. And so this dark line right there is the boundary, right? And it's this dividing line between what I think is inside the system and what I think is outside the system. So this is inside the system, this orange, and then outside the system is the environment. And the environment in closed systems can take a little bit of energy away. In open systems, the environment can add in energy as well. In an isolated system, the environment has no impact on what happens inside of the system. And so it's totally blocked off. That's why I've drawn it with a thick, solid line here, so that you get the idea that there is no way to get anything from the outside into the system. Typically, there's not a lot of isolated systems that we can discuss, but we can get really close to an isolated system, and that's usually what we do. Anyway, so in an isolated system, the total amount of all types of energy and the work done stays constant. So mathematically speaking, it looks like this. So this is the sum of, this big sigma right there, is the sum of all of the energies at time 1. Okay, and that's equal to the kinetic energy at time 1, plus the potential energy at time 1, plus the thermal energy at time 1, plus any work that's being done inside the system. If you add all of that together, you get a number, and it's a number of joules. And it doesn't matter what happens later inside the system. If I come back and I add up the kinetic energy at time 2, plus the potential energy at time 2, plus the thermal energy at time 2, plus any work that it's doing at time 2, I'm going to find that this sum and this sum are exactly the same. And in fact, we could, if we wanted to, define an isolated system by going backwards and saying it is a system that upholds the law of conservation of energy if we wanted to. We can get close to an isolated system over short periods of time by talking about a pendulum, and we're going to do a pendulum lab in here in the coming weeks. And that pendulum, if you think about it, you do work to lift up the pendulum bob, right? So you did work, oops, darn it, there we go. You did work to lift up this pendulum bob. Normally it just hangs there at its lowest point, but you did work to lift it up to a certain height and over to the side. Over to the side doesn't really mean much. But lifting the bob up really is where you did the work. So you have this lowest point that you're measuring away from, and then you can see that it has some sort of a height now away from that lowest point. Now the way this is drawn, this is kind of strange here. So this is sort of a reference line. I am taking it here. I did not make this diagram myself here. And so you're measuring the height away from some reference line, and then you'd have to compare that to the height away from the rest point. So you did work to lift it up away from that rest point. Where does that work go? Well, it's initially kept inside of the pendulum bob as potential energy. And specifically, it's gravitational potential energy, so U sub G. Then when you let that go, that gravitational potential energy becomes kinetic energy as it speeds up, speeds up, speeds up, speeds up. And so at the bottom here, we've taken that gravitational potential energy and converted it all into kinetic energy. And because it's at its lowest point and has zero potential energy, you would think, well, okay, that's where it stops. But the kinetic energy is so great that it continues to move past the rest point and then continues to go up. Now, in an isolated system, the height that you got to here and the height that you got to here should be the same because no friction or damping is taking place. And so therefore, what ends up happening is the kinetic energy that you had here gets changed into potential energy as it gets higher and higher and higher away from the reference line. And so at this point, we're back to having only potential energy. And so under short periods of time where friction can be ignored, you see that a pendulum takes the amount of work done to it initially, converts it into potential energy temporarily, and then back and forth converts it from potential to kinetic, and then from kinetic to potential, and then from potential back to kinetic, and then from kinetic back to potential. Now the total, though, the total potential energy it has here is equal to the total kinetic energy that it has here, which is equal to the total potential energy that it has here, which is all equal to the amount of work that you did in the first place. And so what I'm saying is, if I know how much work was done, I know how much potential energy the pendulum bob has to have, and then I know how much kinetic energy it has at this lowest point. And therefore, I could use that kinetic energy to figure out how fast it's moving at that point. I could then say, okay, well, at this point, it's not moving at all, so there's no kinetic energy. So it all must be potential again, and that potential energy must equal the kinetic or this potential or this work, because it's all the sum of all of the stuff that you put into it is going to be all that you have to work with, right? If I put this work in, that's all I have to do to work with in an energy point of view. Anyway, the formula is a little weird. So sigma E1 is equal to sigma E2 is really the mathematical statement of the law of conservation of energy. It's 8.6 on your formula sheet. I also spelled it out a little bit more specifically. Here I have the kinetic energy at time 1 plus the potential energy at time 1 plus the thermal energy at time 1, which we'll talk about later on, plus the work at time 1 is equal to the kinetic energy at time 2 plus the potential energy at time 2 plus the thermal energy at time 2 plus the work at time 2. And so if I know how many joules I have at the time 1, I should figure out how many joules I have at time 2. Really, that's it. And again, this is crucial. You're going to see this come up again and again and again. And in fact, we could start this class over again using the law of conservation of energy as our basis for our discussion, particularly of items in motion, objects in motion. And then we'd be able to re-explore all those things and redefine all those formulas based off of energy rather than based off of the mathematical definitions that we used. Hopefully that makes sense. If you have any questions, let me know. Thanks for watching.